The extreme value theorem is what we're going to be discussing today. So let's start off by talking about extrema. Relative extrema we discussed a lot when we were talking about derivatives. So let's put a definition down. Relative extrema are points where a function changes from increasing to decreasing, or vice versa. Now, what's the difference between relative extrema and absolute extrema? Well, absolute extrema are the points on a graph with the greatest or least y values. The ultimate max and mins. Absolute max and mins. So let's look at what that means for our graphs. So we have a graph of f of x. What would be the coordinates of the relative extrema? Well, relative extrema, when we're changing, increasing to decreasing or decreasing to increasing. So we're talking about these points, 1, 2, 3, where we're changing direction. So our relative minimum, we actually have two of them. We have this point, -3, 0, and this point, which is -6, 2. Relative maximum is this point right here, -1, 3. Now, on the domain of this function, what are the coordinates of the absolute extrema? So we're looking for the greatest and the least y values. Well, it's easy to see the absolute minimum. It's this point right here, -6. Whoops. I switched that around, didn't I? To -6. Crazy girl. Absolute minimum is 2, -6. Absolute maximum. Well, is this point the absolute maximum? No. Because these arrows mean that this graph keeps going up and up and up and up forever and ever and ever. So there is none. What about g of x? Identify the coordinates of the relative extrema. So we're talking about where it's changing from increasing to decreasing and so forth. Well, we have this point right here, this point up here, and this point here. So relative minimum, let's see if I can do it right this time, is -3, -4, and this point right here, which is 3, 2. We have a relative maximum at -1, 4, right there. What are the absolute extrema? Well, we have an absolute minimum lowest point on the graph. And we have an absolute maximum at the highest point on the graph, which would be up there. Notice that's because the graph stopped there. It did not have an arrow like on F. So where do the absolute extrema occur? Is it always at a relative extrema? On graph F, the absolute min did occur at a relative min. And on graph G, the absolute min occurred at a relative min, but the absolute max did not. Let's look at some more examples. What if we restricted the domain? So what if we only looked at, on F, from -2 to 3? That means I'm ignoring everything else on the graph. I'm putting endpoints at -2. So we're cutting off the graph right there. And when x is 3. So cutting it off here. So we're only looking at this section of the graph. If we cut off the graph to here, not looking at anything else, what would be the absolute extrema? Well, the absolute min would be this point to -6, and the absolute max would be this point -1, 3. What about if we change the interval to -4 to 1? What is the highest point and the lowest point now? Well, the absolute minimum is going to be -4. Did it again. 1, -4, because that is the lowest point on the graph now. And this point up here would be the highest point on the graph now. What if we restrict it on G? So -4 to +5. So starting here and going to here. What would be our absolutes? Our absolute min is easy. That's still this point here, -3, -4. Absolute max. So the highest point on the graph. Oh, it actually happens twice, huh? The absolute max would be at -1, 4, and 5, 4. What about if I change it to -2 to +6? So this part of the graph. Well, that changes my minimum, doesn't it? Because I'm covering up the one that was over here. That's no longer in our domain. The absolute minimum would be this point, -2, 0. And our absolute max, since we stretched out the domain, that point is now our maximum, 6, 5. So what do we notice when we restrict the domain to a closed interval? At what 3 places does the absolute extreme occur? Well, sometimes it was occurring at the endpoints of the closed interval. Could occur when f prime is 0, or as we saw here, that would be f prime is undefined. Sharp turn. So the extreme value theorem states if f of x is continuous on some closed interval, then there exists an absolute maximum and an absolute minimum. On that interval at either x equals the first part, x equals the last, so the two endpoints, or any value x such that the derivative is 0 or undefined. So one of the initial conditions that has to be met to use extreme value theorem is this word right here. It has to be continuous. If it's not continuous, then we can't really guarantee we're going to have a max or a min. Well, these are easy to find when you have a picture, but what if we don't have a picture? So let's take a function, and we're going to start off just reviewing. How do we find where it's increasing and decreasing? Well, that's easy. We need to take the derivative. So f prime would be negative 3x squared minus 12x minus 9. And we want to know when it's 0 so that we can figure out, we can use a little number line to figure out where we're increasing and decreasing and all that good stuff. So I think it's going to be best to factor this. So I'm going to factor out a negative 3. That'd be plus 4x, and that'd be a plus 3 at the end. And we're going to set it equal to 0 so we can find those critical values. Well, this factors nicely. That'd be x plus 3 and x plus 1. So our critical points, our critical values, are negative 3 and negative 1. So let's make a number line for f prime. So our number line, our critical values are negative 3 and negative 1. And we want to find an x value in each of these intervals to test. So in this one, how about let's just go with x equals negative 4. Now notice, we're going to have to plug this in to this factored form. That's the easiest way to do it. And negative 3 is always negative. And if I plug negative 4 into here, that's going to be a negative number. And if I plug negative 4 into there, it's a negative number. So a negative times a negative times a negative is negative. Between negative 3 and negative 1 is negative 2. Negative 3 is always negative. Negative 2 plus 3 is going to be positive. Negative 2 plus 1 is negative. So overall, I would have a positive number. Past negative 1, 0 is a good one. Negative 3 is still negative. 0 plus 3 is positive. 0 plus 1 is positive. So overall, this area would have a negative value. So where are we increasing and where are we decreasing? Well, f of x is decreasing when f prime is negative. So f of x is decreasing on the interval negative infinity to negative 3 and negative 1 to positive infinity because f prime is negative. F of x is increasing on this interval, negative 3 to negative 1, because f prime is positive there. So does this tell us anything about our relative extrema? Well, sure it does. We have a relative, let me reword this. F of x has a relative, we'll start with, how about we'll start with a max. And what's the coordinates? So maximum occurs when we go from positive to negative. So I need to plug in negative 1 into my original function. So that's negative 1 cubed minus 6 times negative 1 squared minus 9 times negative 1 plus 2. Negative 1 cubed is negative, that turns into positive. Negative 1 squared is positive 1, it becomes negative 6. That becomes positive 9 plus 2. So overall, let's see, 10, 12, and a negative 6, that's a 6. So my coordinate is negative 1, 6. And we have to justify our answer. Why is that a maximum? Well, because f prime of x changes from positive to negative. F of x has a relative minimum at, so that's going to be when x is negative 3. So I need to come over here and plug in negative 3 into the original function. Let's see, that would be negative 27, negative 27, which would be a positive 27. Positive 9 times negative 6 is negative 54. It's going to be plus 27 plus 2. 27 and 27 are 54, and we have a negative 54, so overall it's 2. So the relative minimum is at the point negative 3, 2, because f prime of x changes from negative to positive. Here's f of x. Wish we had noticed that earlier, huh? Negative 3, 2, negative 1, 6. what would be the absolute maximum if we're only looking in the closed interval from -4 to -1? So just from here to here. The absolute maximum would be -4, 6 and -1, 6. What would be the absolute minimum on that same interval? What's this low spot right here? -3, 2. What if we stretch it from -4 all the way to 1? Well, that doesn't change my maximums. But does it change my minimum? Yeah, that's definitely the new minimum, because we extended that interval, that domain. So could we do it algebraically as well? What if we didn't have the graph there? So we know what our answers should be, but let's show how we would find those. So first off, we would need the derivative, which we already have, and we already have it in factored form, so I'm going to write it in factored form. There's a couple of things we would want to look for. First thing is we want to know when f prime of x equals 0. Well, we already found those. That's when x is -3 and when x is -1. So we have to test several locations. We need to test our endpoints, and we need to test our critical values. So our endpoints are -4 and -1, and our critical values are -3 and -1. So we need to find f of -4, f of -1, those are my endpoints, and f of -3, which was a critical value. Well, we already have done that on the previous page, so f of -4 is going to be 6, f of -1 is 6, f of -3 is 2. And this tells us where our maximums and our minimum is. So the absolute max is at -4, 6 and -1, 6. And absolute min, is -3, 2, which matches what we saw graphically. If we extend that interval from -4 to 1, well, first we'd want to write down our derivative. We need to state when f prime of x is 0, and that's when x is -3 and x is -1. We need to test our endpoints, which we already had found, but now we have an endpoint at 1, and then we need to test our critical values. Well, f of 1 is -14, f of -3 was 2, and this is 6. So again, I can easily spot my maxes and my min. And this matches what we saw graphically. Now, to be able to use EVT, this one we were able to use it because f of x was continuous, it was cubic. But what about these three functions? If we're looking at the interval -5 to 0, can we use EVT? Well, when I see a fraction, I know that this is going to be undefined when the denominator is 0. which happens at -3. That means we have an asymptote or a hole or something. We've got a break somewhere at -3. So EVT is not applicable. On h of x for -5 to 0, because h of x, let's word it this way, has a discontinuity at x equals -3, which is on -5 to 0. Actually, these should be closed because this is closed. What about this one? Well, we'd have an imaginary answer if this x minus 3 was negative, which occurs, so we want to know, whoops, let me see, we want to make sure this is positive all the time. So x has to be bigger than 3. Oh, the domain of g of x is 3 to infinity. Which means this interval doesn't even make sense. Which means EVT is not applicable since g of x is not defined for the interval -5 to 0. It doesn't even exist there. Okay, what about a natural log? Ooh, this is good review. Natural log. The argument of a logarithm has to be positive. So x plus 7 has to be greater than 0. So x has to be greater than -7. So since the domain of f of x is -7 to infinity, f of x is defined and continuous. On -5 to 0. EVT is applicable. Meaning we could find extrema. So determine the absolute extreme values, provided that the extreme value theorem applies. So the first thing I'd want to do is state that f of x is definitely continuous. It's a cubic. Oops. Now I need to do a couple of things. I'm going to need to find f prime and figure out when it's 0. So 3x squared minus 4x minus 3. We want to know when that is 0. So we can test those critical values and test our endpoints, -1 and 3. Now I happen to know already that this function does not factor. So one way to find your points, of course you could use quadratic formula if you wanted to, or we could type in 3x squared minus 4x minus 3, go to the graph, and we see where its zeros are, where it's crossing the x-axis. I can go second, calculate, 0. And I'm going to narrow down my calculator. Go to the left a little bit. Looks like it's between there and there. Gives me one value of negative 0.535. And the other value, which looks like it's between, I don't know if you knew you could do this, type in 1, and it looks like it's between 1 and 3. It's at 1.869. So I need to find f of x, the original function, at my endpoints, and then at my critical values. Now, even on calculator portions, they want to see this analysis. I know if you had your calculator, you could just find maxes and mins, but they want to see this analysis portion. So to make life easier, I went ahead and typed in the function into y1, the original function, and I'm going to go alpha f4, y1, parentheses, negative 1. I'm going to plug it in. And I got negative 2. I'm going to do the same thing and plug in 3. I'm going to do the same thing and plug in negative 0.535. I'm going to do y1 of 1.869. And now I can see where my values are. So the absolute maximum value is negative 1.121. That's the biggest value. The absolute minimum value is negative 8.065. Sine squared plus cosine. Both are continuous, so I would state g of x is continuous. Now I can show the derivative. Remember, this is really sine of x squared. So that'd be 2 sine x times the derivative of sine x, which is cosine x. And the derivative of cosine is negative sine. Now I'd want to know when that's 0. Gosh, I would not want to do that by hand. So I would check by plugging in the derivative into the calculator. Oops. minus sine x. Now notice it said from pi over 2 to 2 pi. So I would want to change my window to be pi over 2 to 2 pi. And where do I cross? There and there. So 0, left arrow over to get to the left of it. .141, oh, that's pi. And then the other one is over here. .236. Now, since I know I'm going to be evaluating a lot, I'm going to go back in and change this to be sine x squared plus cosine x, because it's so much easier to use the calculator to evaluate. So that's my new y1. I need to evaluate the original function at pi over 2, at 2 pi, at pi, and at 5.236. So I'll start with pi over 2. I'll do 2 pi. I'll do pi. And then, last but not least, I don't know if it's least yet, is, oh, it definitely wasn't least. It's actually the max. So we have an absolute maximum value at 1.25. And the minimum is at -1. So f of x plus 2 to the 2/3, that's a cube root. That is continuous. I'm stating it so I can use the extreme value theorem. So I need to take the derivative, so I might rewrite it. Oh, I don't need to rewrite it. It's already got that. Oh, 2/3 x plus 2, subtract 1, that's going to be -1/3. So that's really 2 over 3 cube root of x plus 2. So this is interesting. The numerator will never be 0. So f prime of x does not equal 0 ever. But f prime of x is undefined when x is -2. Because that would be 0 in the denominator. So the points I need to check -3 in point of 6, and I also need to check this critical value when x is -2. So going back to the original function, I don't really need to use a calculator. Negative 3 plus 2 is negative 1 to the 2/3 can be positive 1. 6 plus 2 is 8. Cube root of that is 2. Squared is 4. Negative 2 plus 2 is 0. So we have an absolute maximum value of 4 and an absolute maximum minimum value of 0. Okay, natural log. So logarithm has to be positive. It has to be bigger than 0. Ooh. So at negative 2 and 2, we have a problem. So EVT is not applicable. Because at x equals 2, h of x is undefined, and therefore not continuous on that interval.